of the lecture, and we'll have a little stub left over for Monday, and that'll be fine. Now we're recording, which is great. We have sound at the source, which is also great. Share application on the screen. Okay, so boom, off we go. Let's see. So where we left off was talking about things like live lock and deadlock and isolation, that sort of thing. Okay, so we'll have a little recap of that, and then we'll get into some other stuff. Eventually, we will get to the two-phase commit model, which is sort of the centerpiece of the lecture. So where we're going to start out, for purposes of discussion, let's say there are two basic kinds of transaction system models. Number one, banking. Okay, we'll call it banking. In a banking type system, everybody is isolated from each other. It is unusual and undesirable in most cases for multiple users to have access to the same account at the same time, right? Obviously, you don't want just anybody looking at your account data. So, and of course, in the case of banking, if you're like a finance major or know something about banking, you might know that banks are required to keep, required reserves on hand. And so, yeah, all the transactions can affect that. But in general, customer activities are isolated and separate. The other one we'll call retail, the retail model of transactions. So in that model, customers routinely share access to inventory, right? So think of a big physical store with a bunch of customers walking around. You wouldn't want in a physical store to say, hey, customer, you can't go down that aisle because there's already a customer there. That would be crazy, right? So in a retail type system, you have to allow for the possibility that a lot of customers are potentially going to be looking at the same data. Okay, so the basic model, starting from that, the models are going to be different. And of course, because that's built into it, you need some kind of policies to keep customers from overdrawing from inventory. So if you think, for example, a seat reservation system, right, whether it's at concerts or airlines, whatever, you have some mechanism where you say, okay, everybody can look at the whole map of the airplane or the whole map of the concert, but they can only pick particular seats, and those are held while they decide whether to get them or not, right? So that's one kind of mechanism. Same thing for Amazon. Amazon says, well, anybody can look at any product page, anybody can add anything to their cart, but there's limits on how much stuff you can add to your cart. And if you don't do anything with it, in a while, eventually your cart gets, restored back, emptied, and sent back to inventory. On the other hand, in a banking system, because simultaneous access is rare and unusual, you can make customers jump through some hoops for when that case happens, right? So you don't have to be super concerned with high performance for that case. Retail transaction processing absolutely does have to be. So there are some basic differences built into these kind of models. Now, next thing, concurrency, right? So we've talked about concurrency, which is just when multiple users have access to the same data at the same times. And what the example I gave of me and my wife at the ATM shows at separate ATMs shows things that can go wrong when people have concurrent access. Now, again, in a retail environment, it's a given that there's going to be some degree of concurrent access. You can't have it the other way, right? It would be crazy to say there are 10,000 people that want to look at a particular product page, but only one at a time can look at it because you've included how many there are in stock, and one person looking at it might add it to their cart and upset things for everybody else, right? That would be crazy. So you have to build in the possibility for concurrency. Now, there are different models for that, different policies. One possibility is the super strict one, right? No simultaneous access to data whatsoever. And for retail, that's generally not suitable, but that Bitcoin hack we talked about, right? I bet those guys wish they'd had something closer to that no simultaneous access model. Alternatively, one thing to keep in mind is that if all the users are just looking at the data and nobody's actually changing it, nobody's writing to that data, it doesn't matter how many people are looking at it, right? Because they're all just going to say the same thing. For example, if you have a web page of purely static content, right, just some big slug of text, and nobody can edit it, it's not like a Wikipedia article or anything, then it doesn't matter how many people look at it at the same time because it's basically a read-only system. You don't have to worry about isolation in that case. So one thing they can get around with that is say, well, any number of users can simultaneously read the data, because reading data by itself is harmless. But you might say, well, if there's more than one viewer, nobody can make any changes, right? That is a strict approach to say that, well, we're not entirely confident that we can prevent things from going wrong. So we're going to say, yeah, as long as there's multiple people logged into the system looking at the same thing, we're not going to let any of them make changes. Depending on the situation, that might be feasible. Again, for something like these online Bitcoin things, something like that probably makes a lot of sense, right? Or you might say changes are permitted if there's more than one viewer, but have to be immediately updated for anybody looking at that. And that's the model that Amazon uses with the web pages, right? I think we talked briefly about Ajax. I know I did a little bit more than briefly in the morning, but remember Ajax, which is not on the test, Ajax is just the mechanism that web pages use to update small little bits of a page. So when you go to Amazon and you look at some product and it says, there's only 12 left in stock, please hurry. And if you buy one, that automatically gets decremented down to 11 left in stock. That's that sort of thing. Amazon can echo those changes really fast to everybody, fast enough that in most cases it's not going to make a problem. Now, which one you choose depends on a lot of factors, right? So number one, how many users there are. If it's a very large, busy system, all else equal, your system is going to have to tip towards ease of use, right? Towards being faster rather than having perfect data integrity. Another issue is the incidence of simultaneous access, right? If you're in the retail model, simultaneous access to data in some cases is just standard, and customers have to accept the possibility that they might be looking at an item, even click on it, but at the last second somebody pulled it out from under them, right? That can happen, and people are disappointed, but that's how it has to be. Second, system complexity and likelihood of exploits, right? If you have a very complex system, right, and even if it's a system designed by really smart guys that know what they're doing, complex systems tend to be vulnerable, right? People tend to miss things. And so if your system is pretty complex, or you otherwise feel that, hey, there's a good chance that somebody's going to find an exploit, right? So for example, suppose there's some, I don't know, stupid online game like some discount Angry Birds clone, right? You're not really worried about people hacking that, right? Especially if it's totally free to play and you're just hoping people show up to click on some ads. Not a big thing. Bitcoin exchanges, though, if you run a Bitcoin exchange, you know that people are looking to find some way to hack you, right? So all else equal, yes, you should certainly be extremely, extremely cautious in allowing simultaneous access. Finally, importance of data integrity versus response time, right? Some kinds of data integrity isn't important at all. We talked about the Facebook case a few times, right? If there are multiple copies of a post stored in different data centers and they're being updated locally and separately, it doesn't really matter if, copy A on one side of the world shows 6 likes and copy B on the other side of the world shows 7 likes for a little while. There's no real damage done. Probably nobody's ever going to notice it. In that case, data integrity is not really important at all. On the other hand, response time can be very important, right? For Facebook. Facebook doesn't want to follow ACID properties when it's delivering people's feeds, because why? Because that's going to slow things down, and Facebook might have hundreds of millions of simultaneous users. They have to have a fast process. They can't take the time to be super careful about, checking that nobody's updated anything while the feed is being constructed. That's just going to slow things down too much for everybody. Again, on the other hand, when you're talking money, though, like Bitcoin, data integrity is hugely important, and you can afford to make people wait a little while to get their Bitcoin. All right. Questions on any of that? Would you like to know more? All right. Well, transaction systems have their own properties that are similar to ACID properties, but implemented a little bit differently, defined a little differently. So for transactions, atomicity means that a group of related tasks for a transaction either gets entirely completed or not at all. So for example, suppose somebody tries to buy something through Amazon. One possibility is that the transaction goes through just fine and people get what they get, and that's great. And at the end, all of the involved databases should show that the transaction happened, right? The transaction should be recorded for the credit card, the inventory should be deducted by one, there should be some supply chain entries showing where the thing is, any relevant analytics on Amazon, like people that looked at this also looked at that, or people who bought this also bought that. That should all be updated. All those databases should point in the direction of saying this transaction was successful. But if for some reason the transaction didn't happen, then again, all of those potentially involved databases should point the way to say the transaction didn't happen, all right? And that prevents the possibility of having one part of your system thinks the transaction happened and another part of the system thinks it didn't, right? In an obvious bad case, Amazon ships you the goods but never processes the credit card transaction. Amazon doesn't get paid. It's the sort of problem that could happen there. Now, ensuring atomicity requires linkages across information systems, right? If you're talking a complex set of systems, even if they're all internal, that's complex enough. But in many cases, they're going to involve ones from outside the organization, right? So for example, credit card payments, or if any of you have heard of just-in-time manufacturing, that was a manufacturing model that became very prominent in the 90s. It had existed a little while before that. So the idea there was, instead of ordering a giant batch of inputs to make some product, giant batch of components, you order the components one at a time as you need them. So every time there's an order placed for a product, in a sense, the manufacturer calls the suppliers who call their suppliers to start sending stuff in through the supply chain, right? And then the idea is just that quality is higher because people are making the stuff in smaller batches and paying more attention. But the point is, in that kind of case, same thing, right? You don't want the manufacturer to call their suppliers or to call some of their suppliers and say, hey, we need these parts, but to fail to call others and be unable to make the product. All right, so that's atomicity, right? A group of related tasks in a transaction, either they're all completed or none of them are. So the databases all point the same way at the end. Isolation is basically the same. In practice, what we mean for isolation with transaction processing is that the users, again, they can see the initial state of the transaction or they can see the final state of the transaction, but while the transaction is ongoing, and some of the systems might show, the transaction is done, and other systems might show that it hasn't finished yet, nobody can go in and access parts of the system because they might get the wrong answers from the database, right? So that's what that means when I say here, intermediate stages of the transaction are not seen by the end users. Now, in practice, isolation is a trade-off with concurrency, right? If you have concurrency, that means people can look at the same data at the same time, which by definition breaks isolation, right? If you are doing a transaction on some set of systems, some set of records within some databases, and there's already one user looking at them because there's concurrent access, right? There's a possibility that that user might get the wrong answer, or they might see the wrong answer in the meantime. So yeah, this is a problem. So you can have isolation, you can have concurrency, you can't really have both. You have to kind of trade off one against the other. All right. Now, what the hell? Oh, what happened there? Okay. Now, we talked about database records being locked to prevent that, right? So locking is a mechanism that helps enforce isolation and helps enforce atomicity. So if a transaction process starts, all the database records involved in that transaction become unavailable to other processes, right? They're locked. Nobody can change them or peek at them, whatever. And that's one way of preventing those kind of database conflicts, because you say, hey, this stuff is in transition. Nobody can do anything with it until that operation is finished, right? And after the transaction succeeds or fails, after it's done, regardless of how it plays out, then the lock will eventually get removed. So if the transaction succeeds, then your credit card will be charged, and then the user can go into their own credit card account and see, oh, I got charged. There it is, right? Or they can go into the supply chain system and say, hey, I wonder when I'm going to get my package. And they say, oh, it comes in, Sunday at 2 p.m., whatever. Okay. But if the transaction fails, same thing, right? There's no point keeping those records locked. If the transaction fails for whatever reason, then it's like it never happened. Okay. Now, of course, high volume or data intensive situations can lock up the system, right? Which is a problem. So locking in some cases can cause real problems. So one thing is if you have many, many processes accessing the same data, right? Imagine if there is some celebrity has posted something on Facebook and it's getting like 200 million views and 3 million likes, whatever. And Facebook feels, oh gosh, every time anybody likes it or anybody views it, we have to perfectly update all those. And anytime anybody is typing a comment, we got to make sure that that comment is fully registered and entered before we can show that to anybody else. When you have that rate of activity coming in, it's really going to slow things down. Likewise on YouTube, right? So YouTube shows video views, right? How many people have watched it? So suppose Rihanna actually goes back to making some music and she puts out a song and it's like a huge hit and 2 billion people watch it the first day. Well, if YouTube tries to keep up with the exact number, right, of video views for everybody who's looking at that page at the same time, again, that's going to be a huge load on their system, right? That is a real problem. They probably won't be able to keep up, or if they can keep up, they'll be spending a lot of money for no good reason, because it doesn't really matter, right? They can approximate the video views or, update them in batches, whatever. But the point is, if you have a lot of different processes accessing that same data, it's going to slow things down. Likewise, you could have one process that accesses very large amounts of data. If you have two massive database tables in your system, and one user does a query that involves the entire tables, that's going to take a while to run, right? That query is running, nobody else on the outside can do anything with those tables, because if they do, the query would possibly get the wrong results. So again, locking is useful for maintaining ACID properties, but sometimes ACID properties are more trouble than they're worth. Okay. Now, concurrency and isolation, in a sense, they're both desirable properties of themselves, right? But we have, concurrency is good. It makes your system easier to use. Isolation is good. It ensures data integrity, right? But isolation also limits scalability. As your system gets bigger, following all those rules is going to slow things down. Likewise, even though concurrency is nice, keeps things going fast, it degrades database accuracy. There's the possibility that two people might try to write to the same chunk of data at the same time, and some of those operations might be temporarily or permanently lost in the shuffle. Now, there is no solution to this problem, right? You got to pick one or the other, or some balance between the two, but you can't have both. It is an inherent property of concurrency and isolation that to the extent you have isolation, you give up concurrency, and the extent you have concurrency, you give up isolation. So Oracle, I haven't linked to an article here with a bunch of different isolation levels for if people are interested in that. And it talks about the same thing, right? Like anybody can read, or you can't have multiple users at the same time at all, or here's our threshold for how fast the updates have to happen if somebody does change something, things like that. But we don't need to go deep into that. I just mentioned the best practice: strict isolation for high value transactions, right? So again, think of somebody trying to withdraw a Bitcoin from an exchange. That is a potentially very high value transaction, right? You want to be real careful with that. You want to ensure data integrity. Concurrent access when the potential losses are small, right? So if you have different Facebook likes on different replicas of data, who cares, right? Doesn't really matter. So potential losses are, pretty much zero in that case. All right. Now, last thing before we get to two-phase commit, rollbacks. So rollbacks are a mechanism for recovering from uncompleted transactions. Essentially what a rollback is, a rollback record, you maintain some record of the state of the system transaction, right? So all the database records that would be affected by the transaction, you make a copy of them and say, here's where we are. And then if something goes wrong with the transaction, right? If some of the data has changed and some of it hasn't, you know how to restore the system to its original state. That's what rollback records are for, right? So basic method, keep a file of all transactions that have been started but haven't been finished yet, and all the associated data with them. If a failure happens, basically you unpack all of those rollback records in reverse, and then you restore the system to its original state. And it's worth mentioning that if those transactions are isolated, right, you can't have more than one going on at the same time. So in that sense, it wouldn't even matter which order you restore them in. But you'd probably still restore them in reverse order just to be safe. Obviously, maintaining rollback record integrity is vital if it's data that you care about. Because why? Because an operation as big as Amazon is inevitably going to experience some transaction failures throughout the day, right? There's going to be cases where, hardware fails, network connections fail, whatever. It is going to happen. And when it does happen, you have to have a backup copy of the data to restore, your original system state, or customers are going to get upset. Either, they'll say, well, we got charged for something, but it never shows up, or Amazon will say, we sent some stuff and the customer never paid for it. Both of those are big problems. Okay. Now, two-phase commit. Okay, so the idea with two-phase commit is you have two or more linked databases that after a transaction, you want them all to point in the same direction. They either should all show that the transaction has finished, or they should all show that the transaction failed. Okay? So, for purposes of this, I mean, obviously we want our system to work correctly and customers to buy stuff, but if something fails for some reason, like the customer entering in a wrong credit card number, we don't want part of the system to think they bought it and the other parts to think they didn't. We want them all to think it didn't happen. Okay, so I'm going to borrow this art. What are you doing? Can it? Oh, try that again. All right. Bum, bum, bum. Okay. So this is fine. Now, the first thing, we have to talk about the players in this game. Okay? So the first one is the transaction coordinator, or the TC. So the TC is an application, what we might call a software agent, but basically think an application that governs the transaction process. Okay? And the resource managers, RMs, are applications that govern a set of one or more databases. Okay, so each resource manager, in a sense, owns one or more databases, and the transaction coordinator tells all the resource managers what to do. Okay? All right, so the way it's going to start, somebody, clicks buy on Amazon, and that launches the transaction process. So the first thing, PC tells the RMs, I'm going to put it over here in request to prepare. PC tells the RMs to pencil in transactions database changes. Okay, whatever's going to happen, we're going to pencil them in for now. We're not sure if it's going to go through. We hope it does, but for now, let's pencil them in. Okay, and obviously I don't mean that literally. I mean that in a way that we can understand. So the RMs at that point tell their databases to pencil in changes and also to prepare rollback records, right? Any rollback records needed. Any needed rollback records. So when all DBs have reported to an RM, the RM tells the TC that it's ready to go. Okay. So the RM the resource manager waits for all of its databases to confirm that they've done this. When they've all done it, the resource manager says, I don't know about the other resource managers, but my guys are ready to do this transaction. Okay? Now, when the TC has heard back affirmatively from all RMs, it knows the transaction is ready to go, right? Because everybody's ready. Everybody's confirmed that they can do this transaction. It's feasible. They have rollback records prepared. Great, okay? Otherwise, the TC will abort the transaction and restore system state. Okay, because if one of the resource managers calls back and says, sorry, we had some kind of hardware failure, our part of the process can't work, the transaction coordinator says, that's okay, we're going to cancel this transaction. It's not going to happen today. They'll try again in a few minutes, whatever. Or the transaction attempt will time out. And again, the system must be rolled back. Okay, so if in a certain amount of time the transaction coordinator just doesn't hear back from all the resource managers, what's going to happen is TC is going to assume there's some kind of hardware failure, or application crash preventing them from responding, in which case, okay, still going to roll back the system. All right. But if we get to this point, the end of the prepare phase, then the transaction coordinator tells RMs to make the changes permanent, right? Everybody's confirmed that they're ready to do this, so the transaction coordinator says, okay, let's do this. So the resource managers, RMs, tell their databases to make the changes permanent and report when they are done, okay? And again, when all DBs have reported to RM, the RM tells the TC that the transaction is done. Okay? Because if all the changes have been made permanent, then we know that things are fine, right? The transaction is done. There's no problem. Once again, when the TC has heard back affirmatively from all RMs, it knows the transaction succeeded and the rollback records can eventually be discarded, right? It's not usually super urgent to throw away the rollback records, but you're not going to keep them for a very long time once you know the transaction is done. So, okay. Or alternatively, right? Or if the RMs don't all report back affirmatively, then again, the transaction will be canceled in some sense. Okay, so that's two-phase commit. And the whole point of two-phase commit is that you have a bunch of different databases that somehow have to make sure that they're all pointing in the same direction after the transaction is finished. And this does it, right? So if the transaction succeeds, all the databases are going to show that the transaction succeeded. If any of them fail, this is going to make sure that the entire process fails, which is fine. Okay. Now, if you're thinking to yourself, wow, that's all pretty complex, I'm just going to point this out to you. This is some Oracle documentation on implementing two-phase commit. This is some of the kind of level of detail I'm sparing you. So you're welcome, okay? What I gave you is a very, very simplified version of the process. But it's an important process to understand. Databases use this. Transaction processing systems use this. And here's just a quick text walkthrough of all that stuff. Okay, would anyone like to know more? All right. So next thing, transaction security. We'll talk briefly about that, and then we'll have a little bit on network architecture. So fraud detection for Amazon. Obviously, fraud detection is important, right? And the way it generally works, same thing as like Facebook detecting spam accounts or your email system detecting spam email. Fake things, right? Fraudulent or fake data, whatever, looks different from non-fake stuff, right? So the system is going to come up with some baseline of what normal data looks like. And if it finds something that's way out of line with that, it's going to get flagged. So like with email, with spam, one of the defining characteristics of spam is that a lot of it gets sent to the same, from the same source to many destinations, and a lot of the recipients don't look at it. Well, you can flag that and get rid of most of your spam that way. Now, Amazon, in terms of fraud detection, does have an advantage because it has literally decades of history it can draw on to see, what kind of transactions are fraudulent and what are not. Now, some of this is going to be based on the customer, and some of it's going to be based on the product itself. Now, before we get into this, let me ask, does anyone know who Mr. T is? What do we know about Mr. T? He does pity fools. What else do we know about Mr. T? We know anything else? I mean, pitying fools is probably the most important thing. We know anything else about him? What do we know about his appearance? He does have a mohawk, or last I saw him, he did. He is a very muscular black man, quite often shirtless, with a mohawk, and he wears a lot of gold. Okay, so I'm going to show you a picture of Mr. T. For those of you who don't know, funny thing. What's that? Yeah. Well, this is relevant, believe it or not. All right, so here's Mr. T, right? There he is. He's got a lot of gold. That's fine. Now, the reason why this is relevant. Okay, normal versus abnormal behavior for a customer. So when I bought my engagement ring for my wife, you know, I didn't go cheap, and I went to the jewelry store, and my credit card was immediately flagged and said, nope, we're not pushing through this transaction until we talk to you over the phone, right? Because I did not have a long history of buying expensive jewelry. But if Mr. T goes into a jewelry store and drops like 50 grand on jewelry, they're going to be like, yeah, whatever, that's Mr. T. That's, you know, that's just a slow Sunday for him. Okay? So it does matter who the person is. Another time I got flagged, my credit card got blocked. I was up late at night and I ordered some front row concert tickets. And then they said, no, for like $1,000 each. And they're like, nope, we're blocking this. You don't get to do that. And I was like, oh, shit. What was the concert? Iron Maiden. Yeah. Anyway. Other things, delivery address, right? So if it's to a different delivery address, that's basically going to be a fraud multiplier, right? It's one thing to have an expensive package delivered to your house in a borderline case, but imagine if you have a somewhat expensive package delivered to an address you've never used before, right? That's going to throw some big red flags. Other things, there are some kind of products that are typical or atypical of fraud. So, for example, things that are easily fenced, like jewelry, like electronics, they're small, they're expensive, they're pretty anonymous. Those are really easy to steal and sell, right? On the other hand, things like books or kids' toys, right? That's going to be a lot more work, right? You don't see people breaking into houses to steal, you know, the xylophone and Goodnight Moon, right? To try to sell those for drug money. Just saying. All right. Other things too, unusual delivery volume. So back when our kids were in diapers, it would not have been unusual for us to order, you know, 4 or 5 boxes of diapers at a time just to get it out of the way. But if we order 1,000 boxes of diapers, they're going to think, oh man, something's up there, right? They're going to think that somebody has hacked our account, and they're going to pull up with a U-Haul truck in front of our house when those diapers land. And you'd be surprised, but people steal shit like that all the time. They steal diapers, they steal baby formula, and you know, they sell it. So yeah, if you ever look, I don't remember how it is now, but like 20 years ago when I was running a convenience store, you know, they had all the city stickers on the bottoms of the packs of cigarettes, right? And what would happen is, you know, people would lift these things and, you know, the guys, they would sell them to other convenience stores, right? They'd lift them from the chains and sell them to other convenience stores. Or they do the same thing. They'd lift like boxes of stuff from Walgreens and try to sell them to some, you know, morally questionable small store. So anyway, fraud detection, theft, it's a thing. It happens. Don't steal. Yeah. Okay. So that's it. Okay. It's good enough for now. Network architecture models. That's our thing. So, right? Question. How do users send and receive data? Well, if you have some kind of system like Amazon, part of it is going to be that the user has an interface where they do their stuff, right? You go to Amazon.com, you type in the products that you're looking for, you add them to your cart, whatever. You have the interface on your side. The business, of course, has to have the data on its side, because if the business doesn't have the data, why are you going there, right? So the question is how the interface reaches the data. So some of those other details are flexible. We're going to talk about 2 major network architecture styles. Number 1, client server, which is pretty much obsolete. I'm not saying you can't find it anywhere in the world anymore, but it's a pretty specialized thing nowadays. It was big in the 80s, started fading in the 90s, and it was replaced by N-tier and its descendants. And we'll have more to say about N-tier. We'll talk a little bit today, but we'll defer some of that till Monday. Okay. Now first, I'm going to show you the picture. All right, so in client server, you have a server machine that a bunch of clients join up, connect to in order to get what they need. Now, in this model, the server might either A, have all the data that it needs stored locally, or it might be connected to a single database machine. Okay, and so all those clients, they need to have everything they need in that server and possibly that connected, database machine, because if it's not there, they're actually going to have to pull a cable out of one of those ports and connect it to a different machine. And depending on how your system is physically located, that might entail, getting a new spool of cable and cutting through walls to access different machines, be a big headache. So that was client server. Again, client server was okay in the days where there wasn't too much data and the applications weren't too demanding, and if you had a set of users that were basically all using the same few applications. It was okay for the 80s and 90s. Now, where are we at? Okay, so yeah, that's what I said with all this stuff here, right? So client server, basic model, clients directly obtain data residing on servers. The application logic, if it's the thick application model, the clients are going to be running the application. If it's the thin application model, most of the heavy lifting is happening on the server, right? Now, there's a couple problems with that. There's a kind of security vulnerability in there, which is that with client server, you're generally granting users fairly direct access to the machines where the data is stored, right? In particular, if all that data is stored there on the server, right, people get access to it. And every user, sure, you try to set up some kind of partitioning system or access limitations where people can't get to data where they shouldn't be able to, but it can happen. But given that client server is generally implemented in systems where it's internal to the business and its employees only, that's not really a huge concern these days. The bigger problem is that it's very difficult to scale or modify. Imagine if you have this one machine and you want to install a bunch of new applications on it because some of your users are using a whole bunch of different kinds of applications, right? Well, in client server, either that means, number one, every server's going to have every application that all the clients are using, which is going to require a lot of resources to do. Or you're going to have to limit your client machines to a very specific set of servers. You might say, well, there's one server that's going to run one application. And if a client wants to use a different application, they have to physically switch over to a different machine, which is going to be a hassle. And that's not even talking about data. Remember, when we're talking about this server, we're saying this server either stores all the data locally on itself or has access to a single database machine. If you're something like Facebook, where you have exabytes of photo data that you need to construct people's feed, that's not going to be feasible, right? Nobody's going to make an exabyte scale database to work with a single server for like a few hundred or a few thousand connected users. They would have to make a whole lot of those. That would be insane. Okay. So it becomes very difficult to scale, right? If the number of applications that you're using become bigger or more demanding, there's ways to do it, but they're all painful ways to manage it. If the amount of data expands to where a lot of different clients need a lot of different data, again, every server is going to have access to that whole range of data. It's going to be a problem. Now, client server, the one thing it has going for it is it's fairly cheap and easy to set up, right? If you've ever played Minecraft, I know some of you surely have. I played quite a bit of it with my daughter over the summer. And, I talked about setting up a server, and I started doing it, and I was like, this is a pain in the ass. I don't really want to do this. So I just went with the LAN configuration, right? Local area network, where you can make your machine available to everybody else on your side of the router. And that's what we did, and it was fine. Right? So that's the same thing with client server, right? Basically, my machine was acting as the server, and if my daughter or my son wanted to join in for some Minecraft, they were like the clients. It was fine. Other advantages, single point for patches and upgrades, right? If the application only exists in one place on the server, it makes it real easy to do the patching and upgrading process, and it's relatively fast. Also, even though, client server offers some unique security challenges, it's also easier to monitor security on a client server system just because the system is a lot simpler than N-tier. Okay, so there's that. The big problems, of course, expansion and modification are difficult. For example problems with that, if you try to add more users on a thin client system where the work's happening on the server, of course, if the server gets busy, performance is going to suffer. Likewise, even if the clients are all running thick applications, right? If the work is mostly happening on the client machines, then what's going to happen? Well, application patching is all going to happen on those individual machines. You're not going to have the advantage of having everything in one place. So these are problems. Another big problem, single point of failure, right? If that server goes down, the client's got nothing, right? They don't have an easy way to connect to a different machine. You have to wait for somebody to bring in a new machine, install the applications, connect it with the database, or you have to, again, pull cables out of the server and connect them to other machines, neither one of which is likely to happen super fast. Okay, so that's client server. And again, client server is pretty much obsolete. You don't really see it much anymore. Again, except for very specialized super secure systems. The other possibility is N-tier architecture. And bear in mind, N-tier has been around for a while, and there have been a number of substantial changes and extensions to it over the last 25 years or so. But if you were a network guy in the 90s and you came and looked at, what's happening with networks today, you'd pretty much be able to understand right away what it was. It hasn't fundamentally changed the N-tier model. It's added on some new technologies on top of it. So this is a good starting point for IDS 200. It'll also be a good ending point. This is really as far as we get into network architecture as we do in this course. So standard N-tier architecture has 3 tiers. Each tier is a set of machines performing the same kind of function. Okay, so in N-tier, the number is typically 3 rather, and it's going to work something like this. So you have your client machines, right? That's where the users are. They're going to say, hey, I want to do some stuff. They send their requests to the application server, right? The application server is where the applications are running, the application server tier. The database server tier is going to process all of those database requests from the application servers. And then we actually have some storage media. Okay, so for example, typical way this would play out, suppose you're going to Facebook and you say, hey, Facebook, I'm logging in, show me my feed, because that's what you do when I log into Facebook. Well, the application server is going to get that request, and it's going to forward that to the database server. It's going to say, hey, show me your top ranked recent activity for, Doug's corner of the universe. And so the database is going to dig, there's not going to be just one disk there, right? There's going to be many, many, many disks. But still, all those disks are going to, somehow pull what they need. The database server is going to find where that stuff is. It's going to call those disks. The disks are going to send the data back. The database server is going to send all that stuff to the application server, which is going to construct that prioritized information into a web page and deliver it to me. Okay? Now, the important thing about this, is that it's set up in a modular way. We'll talk a little bit more about modularity on Monday. I'm going to kick that off the road. But keep in the back of your mind, modularity is important, right? It means that each tier doesn't really need to know the details of the other tiers, right? So, for example, if this application tier gets a request from the client, it doesn't matter which particular machine it's from. What matters is the, it'll get that instruction, it'll process it the same way, regardless of the actual source machine. Okay. Last thing I want to mention about N-tier, typically N-tier is implemented for thin clients, right? Typically thin applications with most of the servers doing the heavy lifting, right? And when you see this in the real world, what you'll find is different vendors give different names to the different tiers. So for a user tier, you might see client or presentation or user. That's all the stuff, or user interface. That's all the stuff that the users do. The application, you might see application tier or server tier or application server or application logic tier, but you'll get the idea that that's where the applications are running. And in a thin, in a thin application kind of situation, you know that the applications are running on the servers. Last one, databases, again, could be called data, database tier, whatever. Again, different vendors have different names, but you get the idea. There's one tier for the users, one tier for the servers that are actually running the applications, and another tier for the database machines. All right, that's all I got. We'll come back on Monday. Yeah.
Real quick, I just wanted to let you know You had me absolutely trembling in my white nights, right?
Why is that?
About these tests and the multiple choiceness of it.
Oh,
And then you said something about the
well, how'd you do?
I didn't study a lick and got a C.
Well, what do you mean you got a C?
I got a C.
Like a 70%?
Yeah, 73.
Well, 73 is actually probably good. I mean, that's probably more like an A minus.
Really?
Yeah, it's not that hard.
No, it's not.
People just got to pay attention and try not to memorize slides. I know.
No, I was nervous.
Yeah, if you get a 73 on the exams and you do reasonably well on the lab stuff, you can do the math and figure out you probably get an A. Though, you know. Yeah. But study harder next time.
I will. Okay, so I was gonna ask, is there any chance we can get the topics of interest for the exam too?
You can email me and I will send it to you. The reason why I don't publish the topics of interest ahead of time is because I find students completely check out during lecture. They think they're just going to memorize all the topics of interest stuff. They generally don't. They try to approach the material in a way that doesn't lead to them really understanding it. So fair warning, that's the times that I did one semester, posted all early, and exam grades cratered. But if you are willing to accept that risk, you send me an email, I'll send you the topics of interest.
Sure.
Yeah.
Just so I study earlier.
Yeah, and I understand.
Thanks so much.
Yeah, no worries. Hello. Okay.
I still didn't get my grade for the
Okay.
exam.
Okay, send me an email. I'll look into it.
Thank you.
Yep.
Same thing here.
All right, send me an email. I'll look into it.
Have a nice day.
Unless you're a Daniel. Are you Daniel?
No.
Oh, okay. There was a Daniel who set that up. Okay. Hello.
I have a question about the month and day. I'm looking at the assignment one day.
Okay.
Do I have to check the boxes for the?
If you want them to display, you have to check the boxes.
Oh, okay.
Thanks, you too. Somebody wished me a good day.
Oh.